I would also like to emphasize that BERD miniseries is only one of numerous workshops we deliver through the UB CTSI. And so many of you and many previous students in the evaluations said, well, I don't know why we didn't talk about this, or I don't know why we didn't talk about that. It's because there's only so much time in one workshop to address the issue. So there are a lot of other important and relevant concepts that are addressed in other series on qualitative research methods, on biomedical informatics, on research rigor. So you can find all this content on our website. If there's something you would like to learn and it wasn't delivered as a part of this series, they're probably delivered in some other series. So we always post a schedule. And for many workshops, we also record, as you can see, we record the workshops and post the content on password-protected website where you can watch them and receive your competencies and certificates in asynchronous modality. If your work required you to stay longer and you couldn't attend the workshop that you're registered for, but you still have to register it. So this is an overall global map. You don't need to memorize it, but just to show you how many different learning options are available. And many of those learning options are actually interconnected. So as I mentioned, there are other mini-series that are offered in the fall or in the spring that are linked to the information and skills that you're going to learn in BERD. So biomedical informatics, teaching, etc. So if you're interested, by completing the by attending all of the workshops, you can receive the certificate of completion for each series. So for the BERD, you will get a workshop if you attend the 4 workshops listed here. If you are interested in CME or CNE, please let us know, and you can receive that as well, up to 6 CMEs. Please respond to the surveys that you're going to receive afterwards. Those are very important to us. Not only this gives you an opportunity to reflect on what you learn and what you hope to learn. We take them very seriously, and we review them and evaluate them every year with the workshop director and also among our CTSI steering committee to deliver new content that's relevant to each generation of trainees, and also to improve the delivery and modality and accessibility of the content that you're going to be watching today. So I will stop here. Questions? Awesome. I'm still here, so text, put it in the chat, and I'm happy to answer any questions. And Dr. Wilding, the stage is yours. Thank you very much.
All right, so just give me 2 seconds and I'll share my slides. All right, awesome. So hi everyone, my name's Greg Wilding. I'm a prof in the Department of Biostatistics, which is in the School of Public Health and Health Professions. And as Katya said, I also direct the BERD, which stands for Biostats, Epidemiology, and Research Design. And we do all sorts of things in the BERD. We do a lot of collaboration. We do a lot of mathematical and computational research in terms of our own methodological developments. And then we do a lot of education and training, which is what this workshop is all about. And today we're talking about sample size and power. So why am I doing this workshop? So what's the motivation here? Critical to study design, right? So if I'm going to conduct some kind of study, one of the first questions is, okay, what is that sample size going to be? It's really critical to what I can accomplish with that design, and I need to be able to justify that number, especially if I'm thinking about grant apps. Now, your sample size is going to be, if you're doing clinical research, that could be the number of maybe healthy volunteers that you need. The number of patient subjects. If you're doing preclinical work, it'd be the number of animals, the number of samples. It's really going to depend on your science. Now, as a statistician, like one of the most common questions I get asked is, Greg, what is my sample size supposed to be? And I always give a very frustrating and kind of typical statistician answer, and it depends, right? So we're going to talk today about what that actually depends on and how you can think through the sample size problem. So we'll start by reviewing the basic concept of sample size and power calculations. We'll talk about how to come up with some of the required quantities that you're going to need, how to do the calculation with software, how to present and justify your sample size, be it in a manuscript, in some kind of protocol that's going to receive review, or in some kind of grant application to some kind of funding agency. And then also what sort of flawed logic that you want to avoid using when justifying your sample size. So what do I need to calculate my sample size? You need a bunch of things, right? You need to think through your study design, because your sample size will depend on that. You're going to need to be aware of what are the outcome variables at play here. You're going to need to come up with the things that you would normally need to do to come up with when you're actually going to do the analysis, right? So I need to understand what are the analysis tools that I will use when I have the data. What are the associated distributional assumptions? What is my alpha level, right? Those are things that I would normally decide on if I'm going to analyze some data. With sample size and power calculations, you actually have to go a step further, and I have to do things like assume parameter values, which can be really challenging. I also have to come up with a targeted effect and also my targeted power, right? So these are all the things that go into the sample size calculation. And I'm going to touch on all of these as we kind of go through this talk. So beginning with study design, Dr. Lamont would have talked about this, the idea that really your study design needs to be tied to your pre-specified scientific objectives. In the sciences, we see really, even though there's really hundreds of study designs one could use in theory, in the sciences, we normally see very simple, straightforward study designs. If you're doing something in the experimental realm, like a clinical trial, right, you'll see parallel group designs a lot. You'll see factorial designs. You'll see crossover designs a lot. In observational studies, you'll see prospective cohort studies, cross-sectional studies, and then also retrospective case control studies, right? So all of those will have different corresponding sample size calculations that would be associated with those. Now, the choice of design will greatly dictate your total sample size requirements, but it's very rare we let that dictate. Very rare that we let sample size dictate the study design. Usually study design is based on other factors like feasibility. There are some exceptions to that. One big exception that I see a lot is maybe the number of groups in an experimental setting, right? So someone might come to me and say, Greg, I want to do some kind of dose response study where I have 4 groups. One's placebo, one's a low dose, medium dose, and a high dose, right? So I have 4 groups there. And then based on some calculations, we see that from a sample size perspective, that's not feasible. And so we might eliminate, 1 or 2 arms. So that would be an example of where I might modify the design. But generally, I'm not selecting design based on sample size, even though sample size is heavily dependent on the design. Now, what you'll see in general is that sample size requirements are much smaller with experimental designs as opposed to observational designs. And the reason for that is in an experimental setting, I have control of certain techniques that I can utilize, such as, for example, stratification, which helps me reduce the variability, which translates to a smaller sample size. So that's why I can get away with a smaller sample size often in an experimental setting. Now, the outcome variable is going to be very relevant in terms of sample size requirements. I'm going to want to gravitate towards variables that are highly sensitive and have low measurement error associated with them. That's going to help me minimize my sample size requirements. Now, your outcome variable, you got to think about how you're going to analyze that as well, right? Again, we're still in the planning stage here. So if I have an outcome, am I going to analyze it in the actual original units of that outcome? Or am I going to transform it, right? So if I'm going to go and conduct a study and I know that my outcome of interest has a right skew to it, well, okay, I'm probably going to apply some kind of log transform when I get to the analysis stage. So I need to implement that into my sample size calculation. A lot of my preclinical colleagues, they might take the rep of some experimental unit, multiple reps of some experimental unit, and then average those, right? And that's the unit of analysis. I got to take that into account. Sometimes we have partially observed outcomes. Like for instance, if you're conducting a trial where you're perhaps treating patients with really bad disease, your outcome could be survival time of those patients. Now, generally speaking, I will not follow every patient until death, right? That would have a end of study timeline, which I could not define ahead of time. And so I may observe the death of some patients, but others, there's going to be some censoring involved, where I only get to see partial information. That's very relevant in terms of sample size calculation. And then finally, I may categorize a numeric outcome. For instance, if it's a weight loss trial, and perhaps I measure BMI as a way of capturing treatment effects, well, maybe my actual analysis will be based on kind of the classic categorization of that variable. So depending on how I work with that variable at the analysis stage, that's going to dictate my sample size. My statistical analysis tools, that should, the ones I use, those should be planned out and be in my analysis plan and usually specified in my protocol. I'm going to have a number of analysis objectives that correspond to my study objectives, and they have to be pretty specific. For instance, I can't just say, okay, I'm going to compare two groups with regards to the mean, right? That's still not specific enough. Am I testing for superiority? Am I testing for equivalence? Am I testing for non-inferiority? They're going to lead to different power functions for a given sample size. Generally speaking, when we're planning, especially in the experimental realm, if I am thinking about sample size, it's usually centered around some kind of primary analysis. There are definitely exceptions to this. For instance, if I'm conducting a pilot study, I might not necessarily have, per se, a primary analysis. But if I can, I generally want to kind of move in that direction. And most of my sample size work will be around that primary analysis, although sometimes we will make minor design changes for the sake of secondary outcomes. It's going to depend on the context and what you're trying to accomplish in that study. Now, for a given analysis objective, I still have to be very specific in terms of the actual statistical technique to be implemented. For instance, if I'm going to test for superiority, compare two groups, I normally will have a number of choices of how I could do that. I could use maybe a two-sample t-test. I could use a non-parametric test. The power, again, is going to be dependent on that choice. And it's also going to depend on the distribution from which the data comes. Now, normally what we will do with a power calculation is if I'm powering for a t-test, which assumes normality, that's the assumption I make during the power and sample size calculation. That's generally standard practice. Now, because there's so many moving parts when it comes to sample size, at this point going forward, I'm going to assume that our study design is fixed, our outcome variables are already selected, and I already know what analysis tools I'm going to utilize. What are other choices I have to make? My alpha level, right? We know our alpha level is that cutoff we need to determine whether a p-value is statistically significant. You might remember, I'm assuming most people have taken some kind of introduction to statistics course, that is also the probability of a type 1 error. You might remember that little 2x2 table that you see there in the lower right of the slide. That your type 1 error, that is rejecting the null when I shouldn't, when the null is actually true, but I still have a significant p-value. So it's really your false positive rate for your study. It's also referred to as your nominal significance level. There's actually a bunch of names to describe the same thing. Now, in theory, you can choose any value you want from 0 to 1, right? Now, are you going to choose some oddball answer? I would recommend you don't, right? You're generally going on a smaller value, right? Because we're talking about an error, right? So we want to have a value on the smaller side. You're going to probably want to gravitate towards a textbook example like 5%. By all means, you can be more conservative and maybe choose a value like 1%, or you could be anti-conservative and go in the other direction and maybe choose a value like maybe 10%. I've seen as high as 20%. You have to, of course, understand that if you consider a higher alpha, by definition, you're going to have a higher false positive rate. I would recommend that, whether you're targeting a particular journal for a paper, or you have a particular funding agency in mind for a grant app, you want to kind of think about who's going to review your plan there and kind of look at either the explicit or implicit guidelines when it comes to selection. A lot of times, if you're targeting a particular journal, they'll tell you in their guidance what sort of alpha level they expect. If you're going to the FDA and you have some study that would be in support of some kind of application to the FDA. They have expectations. You should be aware, if you work within that realm, which maybe some of you do, that the FDA and other regulatory agencies would call this the consumer's risk, is what they call their alpha level. And that term actually makes sense when you think about it. You know, your alpha is your probability of a false positive study, right? So I conclude my new therapy works when it doesn't. That's detrimental to the consumers that the FDA is in place to protect. So hence the name consumer's risk. And so they're going to be very strict about what sort of levels they would allow there. Now, all else being constant, there's this relationship between alpha and your sample size requirement. Anything that you see on red in any of my slides, these are things which I think you can really develop an intuitive understanding of. If I want to decrease my chance of making a particular mistake, in this case, a type 1 error, well, I'm going to need more information so I can make that correct decision. More information translates to me to a bigger sample size. So hence this inverse relationship between alpha and sample size requirements. So what I want to do now is just take a quick second and start to introduce this example, which we'll return to multiple times throughout this talk. This is an example where we're planning a clinical trial to evaluate a new therapy for the treatment of asthma. It's a really straightforward parallel group design where I'm going to randomize N1 plus N2 subjects in a balanced fashion to two groups, one group being a control group, which would receive the standard of care, the other receiving a new experimental intervention. And then I follow them forward in time and then eventually make a formal comparison in terms of outcomes. The outcome that we're going to be working with here is something called FEV1, which is a measure of lung function. And if you've ever been to the allergist before, you might even have taken this test where you blow in this tube as hard as you can. And now the output of that is some percentage that is a measure of your lung function adjusted for patient characteristics like height. So that's our outcome of interest. If I'm starting to think about sample size, I need to think about, okay, how am I going to analyze this once I have the data? Let's keep it simple for the sake of our talk. Let's say I'm going to do a one-sided two-sample test with an alpha of 5%. This is going to address these hypotheses in the middle of the slide here, right? So my null is that the drug is ineffective. The alternative is that the drug is effective. I need to translate that to stat speak, right? So by what I'm going to do here, I was going to say a drug is deemed effective if the average FEV level is higher in the experimental group as compared to the control. So I can rewrite my hypotheses as you see down below here. So this is the classic two-sample t-test test statistic. You probably remember this, right, from your first stat class, hopefully fondly. So it's a function of your mean differences, and then in the denominator, you can see it's a function of your sample size and your pooled variance. I'm going to minimize formulas throughout this talk, so the actual form, don't worry about it. But if I'm going to use a test statistic like that, or any test statistic, I need to understand how that test statistic is going to behave when the null is true, right? In the context of my trial, if the experimental therapy makes no difference, it's just as good as the control, how does my test statistic behave? Now, the reason that you know this test statistic is because someone already worked out the null distribution. Otherwise, you would never have learned it. And so we know in this case that the two-sample t-test has a t distribution as the null distribution. So you know, this distribution describes how that test statistic behaves when the null is true, right? I can see that, okay, if the null is true, my test statistic should be centered around 0, and that makes sense, right? The average should be the same in the two groups on average. And then to decide whether I have evidence against the null, I can set up what, remember, is called a rejection region, where it's this line, in this case, towards the right, where if I'm to the right of it with my test statistic, along the line here, I would reject. Otherwise, I would fail to reject. Now, how do I determine where that line falls? Well, it's dictated by alpha, the decision that you make. So we're going to come back to this example in a second, but what I want to do now is actually talk about power, right? Because this is a talk on sample size and power. Let's actually define what power is. Power is a probability, right? It's a probability of having a significant p-value when I should, right? So the null hypothesis is false, In that situation, I would like to reject the null hypothesis, and power tells me the probability or the percent of time that that actually happens. That's related directly to the probability of a type 2 error. So we talked about a type 1 error, the probability of that being alpha. The probability of a type 2 error, we often denote that by the Greek letter beta. 1 minus beta is equal to power, right? If the null is false, I can either reject or not reject, right? So the sum of those two probabilities have to sum to 1. Now, why should I care about power? Well, think about this. If I am using an assay in a laboratory setting, one property of the assay that I'd like to have is it needs to be sensitive to detect analytes that I'm trying to detect. In an analogous fashion, if I am designing an experiment and there are meaningful treatment effects there in the population, I want to be able to detect it in my experiment. And that's the whole idea of power, is detecting those meaningful effects. And obviously, I want to have a higher value. Now, with type 1 error, I had full control of it. I decide what alpha is. Now, with power, I can't completely control it because it depends on the unknown truths that I don't know, right? In the case of my asthma clinical trial, it depends on the actual mean difference that I never get to observe. But I can manipulate power. And how do I do that? I do that through sample size. So if I want to increase power, all I have to do is increase sample size. Again, power is the probability of a correct decision. How do I increase that probability? Well, give me more information, right? Increase my sample size, and that will allow me a greater probability of making that correct decision. Now, there's a direct relationship between power and what's termed the effect size. I've actually used this term a few times without really defining it. And a lot of you might already be familiar with that term. But if not, effect size is the quantification of the phenomenon that you're trying to study that's associated with the statistical procedure. So in the context of my asthma clinical trial, right, I had defined that really for the drug to be efficacious, I need to see an increase in the mean FEV level. And so my effect size in that situation would be defined by the arithmetic difference between mu1 and mu2. Now, with most statistical procedures, there is this direct relationship between effect size and power, right? So, and again, let your intuition develop here. That makes sense, right? If I want to increase the chance of rejecting based on study data, it's going to be easier if the true difference between my groups is larger, right? As that difference becomes larger and larger and larger, it's going to be easier for me to see patterns in the data. So it stands to reason that power is going to increase as effect size increases. And based on the previous relationship that we talked about, it would then follow that effect size has this inverse relationship with sample size requirements. As I increase my effect size, I'm going to need less information to actually deem the groups different. Now, when I'm doing power calculations, I need to be very aware of how I must express the effect size because it can be done in more than one way. So for instance, I could consider the arithmetic difference between the means, but I could also consider the ratio. So I can talk about, say, maybe a 20% increase in the mean. That might be something that I might consider to be more natural. Now, that's going to be a bit problematic if I'm doing a 2-sample t-test for the analysis, because the procedures for determining sample size dictate that you express the effect size in terms of the arithmetic difference. So sure, I can talk about a 20% increase in the means as being meaningful, but for me to actually do the calculation, I need to translate that somehow to the arithmetic differences. So I need to be aware of that as I'm doing these sort of calculations. Now, as I had mentioned, for sample size calculations, I'm also going to have to assume some parameter values. Now, the idea of assuming something about our populations, that's not new in statistics, right? You all know that, right? You remember from your first stat class that you would have to make maybe distributional assumptions, right? I have to assume that my data comes from a normal population. So that's not new. In sample size calculations, and I mentioned this at the start of the talk, I actually have to take it a step further. Not only do I have to assume the distribution of the data, but I'm going to have to make some assumptions about some of the parameter values. For instance, if I'm using a normal-based procedure, I have to make an assumption about the standard deviation value. And that kind of takes me to what I call the fundamental difficulty with these sample size calculations. If I knew the standard deviation somehow, magically, I probably know the mean difference as well, right? And I probably wouldn't have to do the study, right? I would know everything, right? So the reality is I don't know the standard deviation. So what I have to do is I'm going to have to be able to come up with some educated guesses. And we'll talk about some approaches on how I would do that in the case of the standard deviation a little bit later. So let's return to our example with our asthma clinical trial. Now, how would I compute power for the two sample t-test? Now, with hypothesis testing, if I'm going to analyze the data, I only need to know the null distribution, right? As we mentioned before. That's all I need to do because I'm going to assume the null to be true, and then I challenge that null with data. If I am going to talk about power, if I'm going to compute power, I actually have to know a lot more. I have to know what the distribution of the test statistic is when the null is not true. So this is something I don't need to know when I'm analyzing the data. Now, luckily, a lot of smart people work this out for us, right? There's in the case of commonly used statistical procedures, a lot of these results have been mathematically determined, or they've developed some kind of approximation, or you can use things like Monte Carlo simulation techniques. There's actually a lot of options, and we won't get into the nitty-gritty of that, but you're going to have options available to you. In the case of the two sample t-tests, what we have here, but as before, is the null distribution, right? So this is centered around 0, and this describes how the test statistic behaves when the null is true. And of course, we have this vertical line representing the rejection region. And now what I have is I have the distribution for the test statistic when the null is not true, right? So what might be happening in my population is I might have a test statistic that's maybe centered around 0. And so using this distribution, I can actually calculate the power, right? Because what is power? It's the probability I reject given the null is not true. Okay, well, what is rejecting? It's being to the right of the line, of the vertical line. What describes the probability of being to the right of that vertical line? Well, it's the area underneath that curve, right? So I can actually graphically represent that power. So, that kind of brings up a question, here, because I can see that if I wanted to increase my power, I would just have to move this curve further to the right, right? So I'd have more area to the right of the vertical line. So what actually controls that overlap? Well, in the case of the two sample t-test, it's something we call the non-centrality parameter. It has this form. Again, don't worry about, at this point, don't worry about this formula, right? You can look this up in a textbook, right? Or these are things that are implemented in software. Just look to see what it's a function of. It's a function of the mean difference in the numerator. It's a function of the variance, your variability in the population, right? You can think of that as almost a measure of noise. And it's a function of your sample size. And so the way that this works in the case of the two sample t-tests, as this non-centrality parameter increases, the curves shift further to the right. These curves, they look symmetric. They're slightly right skewed. It doesn't really matter for our purposes. But we can see how we could increase our power, again, by increasing that, what we're calling here our Greek letter nu. It looks like a V, but it's a nu. And so given that, I can see, before we talked about this kind of intuitive understanding of how to manipulate power, I can actually see it mathematically now, right? Because I know that higher values of nu translates to greater power. Well, that makes sense when I look at this function here, right? Because how do I increase nu? I could do it a bunch of ways. One way is I could increase the numerator. I could increase the value of mu1 minus mu2. Right? That will increase my power. And as we said before, generally with statistical tests, if I increase the effect size, that's going to increase power. Right? How would I also decrease the power? Well, one way in which I could do that is I could increase the variance. Right? If I increase the variance, right, the denominator becomes bigger, the whole thing becomes smaller. And I have more overlap between the null and the true distribution underneath the alternative. Intuitively, that makes sense, right? What is the variance? It's a measure of noise. If I'm going to have noisier data, it's going to be harder to see patterns, right? It's going to be harder to come up with a conclusion of significance when I should. And then finally, I can see that if I increase the sample sizes, right, these will become smaller. This whole thing will become larger. This whole quantity will become smaller, right? And again, that makes sense, right? If I increase my sample size, I'm obtaining more information on the population. And hence I'm going to increase my power. So now that we have an understanding of how to manipulate power or how to measure power for a given scenario, the question is now going to come up, what value of the difference am I actually trying to detect? And that takes us to the idea of a targeted effect, which you want to establish in the planning of your study. First, just as a reminder, what's the difference between statistical significance and clinical or scientific significance? Statistical significance is that's all about the p-value being less than alpha, right? I have a p-value that's less than 0.05. That's statistical significance. Clinical or scientific significance, that talks about the practical importance of an effect. So in the context of my asthma clinical trial, what sort of increase in FEV1 would change practice such that we might start using this new treatment? What is the value of that arithmetic difference that would change the field? Now, that's a really hard question to answer. So if you're faced with this particular question, where if you're going to do a sample size calculation, you will be, you can take a few approaches. There are some database arguments. You could look within the publications within your field and see, okay, for the outcomes that I'm going to consider, has anyone established what a clinically meaningful effect is? You'll find that people have done that sort of research. You'll find papers just on that subject. Also, there might be subjective opinions that are kind of shared in your field on what is a clinically meaningful effect. You'll find some rules of thumb that are often used. When I would do a lot of early phase cancer research, for those with really bad cancer, we often considered an increase of 25% or more in survival as clinically meaningful. And that would be the basis a lot of times of our sample size calculations. So if I'm going to go into this sample size problem, what I'm going to first start by doing is establishing what is the minimum clinically or scientifically meaningful effect. What is that smallest difference between the two means that's going to change the field? And we're going to call that our MSME. And so I could represent that graphically with this number line here, right? So this represents mu1 minus mu2. This, of course, will be the null value. And then what I want to do is I want to select this. I want to establish what this value is. Again, I'm not saying it's an easy question, but you have to do this. I have to select what is the MSME such that all values of the effect which are greater are scientifically meaningful, and all values that are less are not scientifically meaningful. And ideally, if I can pull it off, and when I say by pull it off, meaning it's feasible with the sort of study designs that I could implement, that's what I want my targeted effect to be. I want to set my targeted effect for my study, in the case of my asthma clinical trial, the targeted effect to that mean difference in the FEV1 averages that would change the field. Now, unfortunately, in terms of practical stat, right? Because I could sit in my ivory tower and say, oh, we should definitely do that. That we shouldn't conduct a study if that's not the case, right? But in terms of real science, we have to make some compromises because we have some feasibility constraints, right? It's possible that if I set my targeted effect to the MSME, that results in a sample size that's not doable. It doesn't mean you can't do the study. You just need to kind of understand what you're dealing with here. If I have a targeted effect which is larger than the MSME, right? So this is what I can detect in my study. It's in a scientifically meaningful range, but there are values of the effect which are also important, which I cannot detect. Now, is that going to be problematic? Okay, wishy-washy statistician answer, maybe, right? It's not going to be a problem if the actual effect is greater than your targeted effect, right? Because again, all effects that are greater than or equal to the target effect, I can detect. So if the actual effect is here, I'm good to go, right? Where it's going to be problematic is if my actual effect is less than the target effect, but it's greater than the MSME, right? So that means that there's possibly meaningful effects that I'm not going to be able to detect. I'm going to have a study design that's not as sensitive as I would like. Now, you might ask, well, Greg, what if your effect is over here, right? What does that mean? Well, keep in mind that that's less than the MSME. Those are effects I don't want to detect. Those are unimportant effects. So I'm not necessarily worried about those sort of effects, detecting those. Now, given I have an established targeted effect, right? For an ideal experiment, right? What would I like to have? Well, I would like to have it such that if the effect is less than my target effect, I have a non-significant p-value, right? Greater than 0.05, right? And significant results if my effect is actually greater than the targeted effect. Now, unfortunately, I can't guarantee that to happen, right? I'd be really, really in-demand statistician if I could pull that off. I can't do that, right? But what I can do is I can manipulate the probabilities of those happening. And that brings us to the idea of targeted power, right? In terms of target power, you'll often hear this phrase that, okay, this study is properly powered or it's not properly powered. I saw this a lot when a lot of the COVID trials came out, and then all of a sudden the entire general public had an opinion on what was good science. Social media was pretty much a mess when it came to interpreting a lot of the results there. And people would say, oh, this is not a properly powered trial, or this is a properly powered trial. I think it's a very vague statement. Properly powered to detect what, right? If you have a properly powered trial, to me, that means that you have adequate power represented by the green for any effect that's greater than the targeted effect, and you have less than adequate power for any effect that's less than the targeted effect. Because again, remember, ideally, I would not like significant p-values if my actual effect is over here. Now, that's what we would like to shoot for. Sometimes you will have an underpowered study. I'll see this as I review journal articles. You'll see that, okay, for what probably people consider a targeted effect that would be important, the power is not really adequate. For meaningful effects or effects above their target, they have inadequate power. It's not so you have incredibly large effects that you would actually have adequate power. In the sciences, we're very concerned with underpowered studies, right? When people are planning studies, they're very, very cautious about not having underpowered studies. I would argue you should also worry about overpowered studies, where you have sometimes large power for effects that are less than your target. And so you might say, well, why is that problematic? Well, it's a waste of resources, right? There's no reason for me to have a study where I have a sample size that's much, much too large. I'm wasting money. I'm wasting experimental units, like, for instance, patients that maybe have a very rare disease that are hard to recruit into studies. I'm possibly wasting time. So I would argue you should be concerned with both underpowered and overpowered studies and make sure that you're in the properly powered range. Now, I keep talking about, properly powered. Well, what the heck does that even mean? What is adequate power? What should the power be at my targeted effect? Again, as an investigator, that's up to you. That's your choice. What I would recommend is you stick with kind of classic values, because as a whole in the sciences, we've kind of agreed that the minimum acceptable power for a study is 80%. Right? I have no mathematical justification on why it should be 80%, but I think if you're going to go before some kind of regulatory board or a study section and you go in with power of less than 80%, you're going to have problems, right? That's the expectation that people are going to have. Other common values would include 85 or 90% power. For big, large definitive studies, you may even go higher, right? If you're talking about maybe a large pharma trial where they feel they have a promising product and they want to make sure that they can show it to be the case, they're going to invest a lot of resource into that and make sure that they have a highly powered study. So you can have power as high as 99% for targeted effects. For feasibility or pilot studies, some people will go in lower power. I'm of the mindset, or my opinion is that power does not apply with pilot studies. The reason being is that your pilot study is in place to help you plan the bigger definitive study where you will have a properly powered analysis. So for pilot studies, I generally don't let sample size, I don't let that be driven by power. What I'll do is I'll think about other things like how well can I estimate the standard deviation based on that pilot sample size. Now, it's not to say in a grant app that's a pilot study, I won't put some sample size calculation in there based on power because I know reviewers expect it, right? That's kind of less science and more grantsmanship, right? But really, I don't think power really applies in a pilot study, but that's my opinion. Now, one thing you should think about when you're trying to decide on what power should be is you should think about the consequence of a false negative study, right? Because if you have inadequate power, what does that mean? Again, you're not rejecting when you should, right? So you have a false negative study. I think you should think about what are the consequences of that. Are you going to miss out on an incredibly promising line of research? Does that put an end to that line of research? In that case, that might tell me I might want to increase the power a little bit more if I can pull that off. If that's not the case, then maybe I'm willing to accept lower power. In terms of regulatory agencies, again, those that are conducting studies that might be relevant to the FDA, one thing to keep in mind with power is 1 minus power in their own guidance, they call that the sponsor's risk, right? Again, what is 1 minus power? It's a probability of a type 2 error, right? So I'm failing to reject when I should. That hurts the sponsor, right? The FDA and other regulatory agencies are not going to pay as much attention to that because they know that that's really on the sponsor to make sure they're properly powered. They're very concerned with the probability of a type 1 error, which I said before is the consumer's risk. The sponsor's risk, again, that's going to be on the sponsor. They're going to be naturally motivated to make sure that they're properly powered. All right, so I've talked about all these things that go into sample size, and I've yet to do a sample size calculation. So let's actually do a calculation here. Regardless of what procedure you're going to use, again, you're going to input your significance level, your targeted power, your targeted effect size, and any additional statistical assumptions. And it's going to go through some kind of mathematical machinery. The specific mathematical machinery, because I'm talking in very vague terms about this, it's going to depend on your procedure. And again, you can find a lot of stuff implemented in software, and then we'll touch on software a little bit later. But out of this mathematical machinery is going to come your sample size. So let's actually go back to our clinical trial again, our asthma clinical trial, and let's say that it's been established somehow that a meaningful effect is 2 units, and that our standard deviation that we can assume here is 4 units. As before, I'm going to use the alpha of 0.05, and I'm going to make the decision that I want to have 80% power, meaning that my probability of a type 2 error is 0.2. So I enter these following quantities in my favorite statistical package that allows me to do things like calculate sample size. And I'll get a result like this, right? So if I input all those values, and I'll duplicate this calculation in a software in a little bit, and what we wind up seeing is I need 51 per group. Now, a lot of softwares will give you a plot like this. I like calculating a plot like this when I'm working with investigative teams during the planning stage. What this shows is the relationship between power and sample size for this specific scenario. Now, I would never be able to guess exactly what this curve looks like, but I would know that it's going up based on what we've talked about before. If I want to increase the chance of me making this correct decision, if I want to increase power, I need more information. I need a bigger sample size. So if this curve was going down, I screwed up somehow, right? I made a mistake with the software. And so I can see where 51 is actually coming from. If I go to 51 on the x-axis and go up, that's where it actually crosses 80% power. And I can also use this graph to see, okay, if I want higher power, what is the sample size requirement? What if instead of 80%, I wanted 90% power? Well, all I have to do is just go over to the curve and then just drop down, and it's around 70-ish, right? Is what I would need, and that's per group, right? So I need 140 total. Now I'll also construct a plot like this. This is a good plot for things like grant applications. So assuming I have the room, and of course that's always a challenge in a grant application. this is a good figure, I think, to include, right? And so what is this showing? This is showing the relationship between power and effect size. Now, in my calculation, I had selected an effect size of 2. What might be of interest to the reviewer is, well, what is the power for other effect sizes? Because maybe they disagree. I went into this saying that 2 is kind of like the minimally important effect between these two groups, but maybe they think that's too small, that's not going to move the needle, and they're thinking more along the lines of maybe 2.5. And so this plot is useful in the sense that it provides all that information. If I go to an effect of 2.5 and I scroll up, I can see I have about a 93%-ish power in terms of this particular procedure based on a sample size of 51 per group. So I recommend this as kind of a good graphic, assuming you have the room for it. So what I'll do now, before we actually jump into some software usage, is I'm going to take just a pause here and answer maybe a few questions.
Yes, I just wanted to clarify something.
Yeah.
Can you go back 2 slides maybe on the graph where you went to 90% and you came up with the number 70 and you said it's actually 140 because you need 1 for each what end, you said?
Yeah, because the x-axis is sample size per group. You know, I could have total sample size there too.
Gotcha. Thank you.
Yeah, no problem.
Anybody else have any questions? Thank you, Jillian, for asking yours. I do have actually, Dr. Noyes is asking, when is the right time to consult a biostatistician if I'm planning a study?
Oh, at the end of the study, we already have the data. No, I'm just kidding. No, you want to consult with the statistician at the very beginning. It's actually most important that you consult with a statistician then. At the university, and I also work outside the university as well, so I work with a whole range of different sorts of individuals. Most of my job is during the planning stage, right? So in terms of determining sample size, what statistical techniques to implement, what sort of analysis plans to implement once we have the data, that's all the work I do at the very beginning. Never wait to the very end to consult a statistician. If you're well-versed in statistics, then maybe you don't need to talk to someone like me, and that's fine. But if you have a question, when in doubt, talk to your friendly statistician, because I've analyzed a lot of doom studies in my day. I probably have worked with every department at UB, and unfortunately, I get a lot of data sets that, you know, they've collected the data, they didn't think to talk to a statistician until they had the data, and it's too late. I can't save them. I can implement some fancy techniques, but if you're not properly designed, in this case, in the context of what we're talking about today, if you're not properly powered, I can't save you. So luckily here, UB, if you're a UB a researcher, you have a resource available. You have the BERD. A lot of people don't have access to statisticians. So I invite researchers, you know, whether you're junior or established, always consult with statisticians, especially anything involving a grant app, anything where people are going to be evaluating your research. And even if that's not the case, if you want to have a good paper, just consult with a statistician. If you think you already have it right, talk to them anyways. They'll be like, yeah, you got it. Yeah, that's exactly the way I would do it.
Now we have another question. What if they don't have funding to pay a biostatistician? What do you recommend?
Yeah. So it depends what you need a statistician for. You know, with the BERD, if you're talking about the analysis of data, or even just if you want to talk to us, you get 10 free hours. I'll be honest, I haven't charged anyone yet, because if you go over that, I'm you know, go to 12 hours, I'm not going to charge you for that, right? It's kind of just in place to keep people from asking for 100 hours of free time. Again, you have this resource available to you. If you're working on a grant app, like, so if you were going to send a grant to the NIH and you're looking for a co-investigator, I would never charge you for that, right? We're both going to be written into the grant, as, you know, you'd be the PI, I'd be a co-I. So you generally will not have to pay for a statistician unless you have large data needs. So we'll have some people that come to us and they need a couple hundred hours, and a lot of times we might pair them with a PhD student who has a master's in statistics and they work on their project.
Excellent, thank you. Should investigators email you directly to reach out to the CTSI, or is there a someplace else that they can go to?
Yeah, no, great question. It's actually my last slide. I talk a little bit about the portal, and so you can send a request to me through the portal if you're requesting CTSA services of really any type. It's not just the BERD core. There's other cores there as well. That actually gets directly emailed to me. If you have some kind of question and you don't think it's really related to what we do in the CTSA, you could always email me directly. And I'll have my email at the very end as well. But I'm easy to find, just Department of Biostats at UB under the faculty.
Excellent. Thank you. Does anyone else have any questions?
All right, so moving on, let's talk about how you're actually going to do these sort of calculations. You're going to do this by hand, right? That'd be crazy, right? So you're going to use some kind of software, and so there's a lot of software available. Just starting with what's commercially available, there's something called Pass. Actually, I use that. Now it's a little expensive. I think it's $1,700, and that is a perpetual license. Still expensive. I do sample size calculations all week long. So for me, it makes sense. It might not make a lot of sense for a lot of you, but that is something that is available. It's a great software package. There's something called Inquiry. There's something called East. East is something I would love, but it's really expensive. It's about $8,000 to license it a year. That's only for someone that would do like complex adaptive design. So for I think most of the audience, that's nothing you'd be interested in. If you already have a statistical analysis software on your PC, you might already be able to do some of these calculations. If you're a SAS user, as some of you might be, there's something called Proc Power and Proc GLM Power. If you're an SPSS user, there is something, at least last time I checked, called Sample Power, which I do think you have to pay extra for. If you're a Stata user, and Stata is a great program. If you're a non-statistician, you're not really a coder, that's actually the software I recommend you consider. It's kind of based on pointing, clicking, and it does a lot of, I think in my mind, a lot of solid analyses, and it's very straightforward. Within that package, there are ways to do sample size calculations. But you really don't have to pay for anything. There's a lot of free stuff on the web. I think for most people on this call, that would be fine. There's something called G-Power. We're going to actually use that on the next slide. There's something called PyFace, which has a great name. There's also something called ST-Plan, something called PS. There's a number of web-based calculators out there. I would just caution you that if you're going to use a web-based calculator, make sure it's associated with a reputable institution. Like anything that you get for free on the web, you always have to be a little bit cautious. And then there's the open source R statistical software, which we might have some R users on the call. There's all sorts of great functions for computing sample size calculation. I actually use R a lot for doing sample size calculations specifically. Now, one thing I do want to point out here is that if you use two different softwares for the same problem, you might get a slightly different answer. Now, it doesn't mean that one is right or one is wrong. It's just that these different software packages might be using different approaches to get at sample size. Now, when I say there might be a difference, it's going to be very, very small, right? I'm not talking that one package is going to tell you 51 per group and the other one's going to tell you 551 per group. Not anything like that. It's like 51 versus 52 per group. So just be aware you might get slightly different answers with some of these softwares. So let's actually use G-Power here. G-Power, I think this is the one I recommend most to people, a lot of my non-statistician colleagues, because I think it's a really solid program. I think it's pretty straightforward, and it does most calculations that you would probably need. And when I think about the average researcher, you can download it at this link. Don't feel you have to copy this link. Just put in G-Power into Google and it'll be in the first couple links. So it's really easy to find. And let's kind of go through how I duplicate that calculation for our asthma clinical trial using G-Power. So if I open G-Power, I download it, I open it, I'm going to get this screen here. The first thing that I'm going to do is I'm going to make sure that my test family is set to t-test, because I'm going to use a 2-sample t-test in my asthma clinical trial. Now, there's many different t-tests, as you know. I'm going to use the one where I'm testing for differences between two independent means. And then in terms of type of power analysis, it can do a few different things. I could determine the power for a fixed sample size. I can determine the effect size for fixed power and fixed sample size. What I want to do is I want to determine what is the sample size I need. And so I'm going to make sure that the type of power analysis is set to compute required sample size. Next, I'm going to specify my input parameters. I'm going to set tails equal to 1. It's a one-tail test. And then you'll see this one box here for effect size D. D here stands for Cohen's d, for those that are familiar with it. That's the mean difference divided by the standard deviation. Now, you could compute that really quickly on a piece of paper, or you could actually hit this determine button, which when you hit that, it opens up this little side panel. And in this side panel, you can enter in your values. You can enter in your two hypothesized means and the standard deviation. Now, you might say, well, Greg, I don't necessarily know the means. I just know the mean difference. That's okay. That's all that's actually required here. So whether I enter in 0 or 2 or 100 and 102, it's the same mean difference, and I get the same value of Cohen's d. So really, if I was designed G-power here, I wouldn't ask for individual means. I would just ask for the difference, but that's the way the software is. So if I enter in 2 means such that the difference is 2, what we decide is a clinically meaningful difference, and I enter in my standard deviation of 4, which I specified before, and I go ahead and calculate that, it's going to throw that value in the box. That 0.5 was actually what was already there just by coincidence. That's the default value. But most likely your value is not going to be equal to 0.5, and so you'll have to replace that. Next, what I do is I then make sure that I have my alpha level of 0.05 specified correctly. I have my power. I've decided that I'm going to use 80% power. And then I have my allocation ratio. The ratio of my sample size is set to 1. I want to have a balanced design. I specify that, and then I hit calculate, and it gives me this output that you see here. And then you can see where I got that 51 per group from for a total of 102. It gives the actual power here. I guess one thing I forgot to mention is that, if I specify 80% power, it's going to give me a sample size. The exact power will not be 80%, because keep in mind that sample size is discrete. I can't have 0.3 of a subject, right? I have to round. And so the way that we normally do it, and this is the way the software works, is that it's always going to round up so you have at least the power you specified. So with 102 total, that's going to give me about 81% power, that's fine, right? I had asked for 80, I got 81%. That's fine. I also get this value, the non-centrality parameter. We had called it new. It's called delta here. And here's the critical value for defining a rejection region. These are things that you don't necessarily need, I think. It gives you, and this is an aspect of G-Power that I like. It gives you this little graph that was very similar to the one that I showed on the slide. Again, I'm not going to throw that in a grant app, but that helps me understand that, okay, that the calculation that I did actually makes sense. It might help me understand if I made a particular mistake. So I always like to have a number of checks in place to make sure I don't screw up, right? With point and click software like this, it's always easy to make a mistake. Now I can also request from G-Power some additional plots. If I hit that button at the very bottom there for XY plot, it will open up this panel. And then using this, I won't go through all the details of this. I'll let you play around with the software later on your own. I can go ahead and create a plot like this where I'm looking at the power as a function of total sample size. I could also create a plot there for maybe power as a function of effect size. As I said, that might be something you would want in your grant app. This is not really a publication quality graphic. That's okay. What I can do, and I don't have a slide for this, but if you click on this tab here, it will give you the data that was used to create this plot. And what you could do is then take that data, copy and paste it, throw it into Excel, and make a nicer plot. So that's something you could play around with as well. So as you can see, using G-Power is really straightforward. Now, it's always a good idea to do what I call a sensitivity analysis. Now, what does that mean? Well, when I calculated 51 per group, that was based on just a set of values that I made a decision about. Now, during the planning stage, I might have some uncertainty about those values. And so in that situation, it's a good idea to kind of see how does the answer, in this case, how's the sample size that I need, how does that change as I let these different values vary? Now, because of all the moving parts, you can't let everything vary, right? So what I might do is I might fix the effect size because I have this established clinically meaningful effect size. I'm not going to play around with my alpha. It's going to be 0.05. I'm not going to change that. I'm not going to change the number of sides of my test. So I'm going to fix some things and then let other quantities vary. Here's an example of what I might have done for our asthma clinical trial. What I'm looking here is I'm looking to see how does the sample size per group vary as I let standard deviation vary. And then I'm also looking to see, what is the required sample size if I maybe want to increase my power from 80% to maybe either 85 or 90. And so on this plot, I can see where I got my original sample size. Remember, I assumed a standard deviation of 0.4. And right there, that's where that 51 came from. If I wanted to increase my power to 90%, and we kind of saw this with a different graph, that's where I'm going to need about 70. Now, what if I'm a little uncertain about that standard deviation value? And instead of 4, maybe I'm thinking, oh, it could be around 7. Well, I can see how the required sample size changes. Again, I would never be able to guess what this graph looks like exactly, but I should know that that's going to go up, right? As the data becomes more and more noisy, the sample size requirements are going to become higher for me to see the patterns in the data. So specifically, if my standard deviation is 7, and if I want 80% power, I'm going to need to about triple my sample size. I went from about 51 per group to a little over 150 per group. So I can use this to help brainstorm in a interdisciplinary group as we're kind of talking about how we're going to go forward with our experimental design. A graph like this can be really, really helpful, and it can really help you understand how sensitive your sample size is to these different choices that you're going to make. Now, one thing we're seeing here is that sample size is really sensitive to the standard deviation. And so really determining the standard deviation when I have a numeric outcome, that can sometimes be the most difficult part of the sample size calculation. And so over the years, I've kind of developed a number of strategies to kind of deal with this. And they kind of fall in these 3 different buckets, going from worst case scenario to best case scenario. The first being our investigators' experience or best guess. You can imagine that kind of sounds horrible, right? Just by the very title. Next will be literature review and then pilot data. And let's talk about all 3 of these. So investigators' best guess. This is not ideal. This is not where I want to be. But you are in situations sometimes where you're challenged with coming up with a sample size for your study, and you have little to no data to justify a particular standard deviation estimate, right? It's maybe an outcome that hasn't been used that often in the literature, or maybe it hasn't been used in a patient population like this at all, or so some kind of subject population. You might be in a situation where you have to do your best and come up with a good guess of what that standard deviation is. Now, you can use what I'm calling them statistical tricks here, but they're mathematically based. One thing that I can do is I can use the empirical rule. You might remember that from your first stat class when you were first introduced to the normal distribution, where they would say things that, okay, between plus or minus 2 standard deviations is 95% of the data. Okay, how can I use that here? Well, if someone with a vast amount of experience dealing with this patient population and maybe this particular outcome, if they say most of the data is between some number A and some number B, well, then I might say, well, okay, well, what do you mean by most? If they say that most means to them about 95% of the data, then, okay, maybe 5% of the time you'll have some unusually large or small values, but 95% of the time it falls between these 2 numeric values. Well, that tells me that my standard deviation could be estimated by the difference between those 2 numbers divided by 4, right? I'm just using the empirical rule here. And I can come up with a guesstimate of what sigma is. I'm not going to tell you that's a great estimate, right? But that may be the best that you can do. Another approach is someone might tell me, well, Greg, I have no idea what the standard deviation would be. But I know just from my clinical practice that all the data is between these two values, X min and X max. Now, what they've given me essentially is an estimated range. Now, how can I use that to get at the standard deviation, right? Because my sample size calculation is not a function of the range, it's a function of the standard deviation. Well, I can use this mathematical result, super old, right from the 1950s, where this guy showed that the standard deviation is mathematically bounded by the range divided by 2. And so if I want to take a very conservative approach, I can use that quantity in my sample size calculations as kind of almost like a worst case standard deviation estimate. Some people have made the case that that's too conservative, that you're going to wind up with a sample size that's just much larger than you need. And I think there's a lot of validity to their arguments. And they've made a case that, take the range and divide by 4, and you're going to come up with a more reasonable answer. Again, all of these are not the best estimates. These are not things I recommend given you have options. Ideally, or better than this, I would like to use the literature. If I can find, not necessarily the study you're planning, but a similar study, looking maybe at a similar population, what I can do is borrow their standard deviation and use it in our own calculations. Now, that sounds like a quick fix, and I'll be honest, sometimes it can be. But you still have to be really careful here. You have to ask yourself that this similar study that I found in the literature, how similar is it actually to the study that I'm planning? Is what I'm planning an experimental study and what I found in the literature an observational study, which may be more variable? Are they truly dealing with the same outcome, measured at the same time under similar circumstances? Are the populations they're studying similar to the population that I'm going to study? For instance, am I going to have similar demographics? If we're dealing with patients here, are they being treated in the same country or a similar country where you might have different healthcare systems? If I'm dealing with patient subjects, are these people that have the same sort of disease severity? Were they observed under similar settings in the context of my asthma clinical trial? There's going to be a seasonal effect that always comes with asthma studies. Was this study in the literature going to be similar to mine in terms of things like that? These are questions that you have to ask yourself when you consider borrowing their standard deviation here. Now, one challenge you might face is the standard deviation might not be explicitly given in the paper. And so why is that? Why would I not have a standard deviation there? Well, the standard deviation is often referred to as a nuisance parameter. It's not something that we're necessarily interested in from a scientific perspective, but it's part of the problem. So I have to estimate it as a statistician, but that's not necessarily a quantity that maybe readers would be interested in, and it doesn't make its way into the paper. So what can you do in that situation? What you might have to do is some back calculation, because even though the standard deviation might not be provided in the paper, I might have quantities that are based on the standard deviation. For instance, in a paper, if the mean and the confidence interval for the mean is provided, well, I know the formula for the confidence interval for the mean, and I know it relies on the standard deviation. And I can do some back calculation as I'm doing in this numeric example here and arrive at a standard deviation estimate, even though it wasn't explicitly given in the paper. In the paper, instead of the standard deviation, maybe they gave an alternative measure of variability such as the interquartile range. Well, in that situation, talk to your friendly statistician. There's a lot of mathematical relationships between quantities like that, and you can derive an estimate of the standard deviation based on the interquartile range. You also might end up in a situation where you have multiple papers that you might be able to extract standard deviations from. And in that situation, what we'll often do is we'll often pool these different sources using meta-analysis techniques. Now, with any meta-analysis, and you probably have heard this before, you always have to be cautious. You got to be cautious when you're combining data from different sources. But that is something that you can consider doing when you're trying to get at that standard deviation. Now, the best case scenario in my mind is a pilot study. Okay, so why would I prefer a pilot study in terms of obtaining the standard deviation? Well, if I'm conducting a pilot study, generally speaking, I'm conducting a study that's going to be very, very similar to the study that I'm currently planning. It's going to be conducted under similar conditions. The data quality is going to be very similar. The population that I'm sampling from is going to be very similar. It's not going to be identical, of course, right? But a lot of the sort of biases and variabilities that I have to deal with when I'm using the literature are maybe not necessarily here with pilot data. Now, even though that's kind of, in my mind, a best case scenario, it doesn't mean that you're not going to have potential issues here. Keep in mind, when I'm doing a sample size calculation for numeric outcome, it requires sigma, the true standard deviation. What I'm doing here is I'm plugging in S, it's estimates. That is variable. And the problem is with a pilot study, a lot of pilot studies are fairly small. So even though I have an estimate of the variance of the standard deviation, I'm going to have some variability there. It might not be the most reliable. And so in that situation, you can consider maybe perhaps using not only your pilot, but also the literature and kind of come up with some kind of compromise estimate. You could also, this has been a strategy proposed by some, is instead of using your estimate S as your value for sigma, compute a confidence interval for S and use that upper bound. That's kind of taking a conservative strategy to this particular problem, and that's a strategy that a lot of people implement. I just want to talk a little bit about missing values and how you need to really think about that in terms of your sample size. If you've conducted science previously, right, missing values happen, right? It'd be very rare that I get a data set that has 0 missing values. That can be the result of, study personnel mistakes. The sample wasn't, processed properly. There was some contamination. Also, if you're doing clinical research, sometimes subjects just drop out, right? They disappear, right? They lose interest. They could die unexpectedly, right? There are multiple reasons why you might have missing values. Now, in terms of the analysis data, the analysis of the data, I can still analyze what I have, right? So luckily, I can still analyze my data, even though I might have some missing data. And I'm going to have some reduction of power. Generally speaking, the reduction in power is not necessarily going to be that bad, right? So if I have a data set and out of the 100 subjects, 5 of them went missing. So instead of 100, I have a sample size of 95. You're not going to see a big reduction in power. That's the good news. Now, there are some more complicated issues that probably are kind of beyond the scope of this talk here, but I just want to touch on this, is that, there are issues around biases. Now, if I have missing data, especially if we're talking about like clinical research, if data is missing, we often have something called informative missingness in statistics. And that means that the reason that the data point is missing, that's related to the value of the outcome had I observed it. Now, what do I mean by that? For example, if I'm dealing with a maybe very sick patient population, right, in maybe oncology, and I notice that I have some missing quality of life measurements, most likely those particular individuals are not doing as well as those that do not have missing data. And so even though I can still analyze what data I have, there is a bias that's entered into the analysis. That's nothing that I can really address. There are some fancy methods that you can use, but they have their limitations. Now, you might say, well, Greg, can't you use imputation methods, right? These are very commonly used in the sciences where I replace the missing values. So of those 5 people that disappeared in your data set of 100, just use some imputation values, and now you're back to a sample size of 100, right? And you're probably familiar with some popular imputation methods. Probably the most popular would be last observation carried forward, which is commonly used in longitudinal data. It's actually been shown it can make things worse, right? So even though I'm replacing this missing data and getting back to the original sample size, sometimes that actually makes the problem worse. I would have been better off just analyzing the data I had. And so that's been shown in the statistical literature. So you have to be really cautious with these imputation methods. Now, if I know that in my study I'm going to have some missing data, I got to work that into the sample size estimate. And that's what we refer to as a sample size adjustment, which is kind of a vague term here. And essentially this equates to just inflating your sample size to allow for the missing values. When I use G-power and I calculated that sample size of 51 per group, that's what I need for the analysis. That's what I need to end up with. Now, if I conducted a pilot beforehand, I might have a good sense of how much of the data will go missing. And so what I can do is I can take the sample size that I need for the analysis as computed by G-Power, and then I can take the percentage, which I'll call P here, of the amount of missing data. If I take my sample size from G-Power and divide by 1 minus P, that's going to inflate my sample size such that I'm covered. And as a numeric example, I needed 51 subjects in my asthma clinical trial. If I have good reason to expect I have 20% missing data approximately, I won't know for sure until the study happens, but based on previous studies in this population, based on my pilot data, 20% is a reasonable number. I can divide 51 by 1 minus 20%, which is where that 0.8 is coming from, and I see that I'm going to need 64 per group. That's the sample size I'm going to use for enrollment in the case of my cancer clinical trial. Now, because of limited time, I can't talk about all these scenarios. We kind of focused on, numeric outcomes in the context of a 2-sample t-test. Almost all those concepts translate to these more complex problems. We did talk about binary outcomes. With binary outcomes, there is this extra complication that the sample size doesn't just depend on the difference between the proportions in my 2 groups when I have a binary outcome, but it actually depends on the actual values. So mathematically, it's a little more complex of a problem. So that's something that you would have to contend with. With regression modeling, right? I might have a study where at the end of the day, my analysis is regressing some Y variable on a collection of X variables. My sample size is going to depend on the relationship between all the X's and Y and the relationship between the X's. So there have been a number of strategies that have been developed to handle that. And so, but that is something that you're going to have to look into, right? If that's what the appropriate analysis is for your study. And so you got to think about how I actually address that from a sample size deriving standpoint. Longitudinal data, right? With longitudinal data, if you're not familiar with that term, I'm collecting data on study units over time at multiple time points. Those time points may be, equally spaced. They may not be equally spaced. Either way, the complication here is, in terms of sample size, is I have many more nuisance parameters. Not only might I have different variances at the different time points, but I now have correlated data. Right? Correlate is if I take multiple measurements on the same study unit, they're going to be correlated with each other. So now I'm going to have to specify some values for those correlations. Multiple testing problems, right? Multiple testing can take the form of the comparison of multiple groups. It can take the form of sequential analyses. I might have co-primary endpoints. There's more correlations that I have to deal with there. I also have complications with things like non-inferiority or equivalence testing. Time to event analyses, where I'm dealing with partially observed outcomes. Not only do I have to worry about, say, the survival time, but I also have to worry about the sensory mechanism at play. And then I also have estimation objectives that I need to worry about. I'll skip the part about unbalanced designs because I know we're running short on time here. Some of you may be dealing with things where your sample size is fixed. That's a commonly encountered scenario, where maybe my analysis, I'm submitting a grant and it's based on already existing database. The question is no longer about sample size, right? The sample size is fixed. It is what it is. In that situation, what you now have to do is you have to determine what is a detectable effect size. So you have to kind of work backwards using that same mathematical machinery and figure out what sort of difference between my 2 groups can I detect, and is that realistic and is that clinically meaningful? Right, that would determine whether you'd want to go forward with that study. What I want to do is just kind of, maybe I'll skip this. These slides will be publicly available. This is a checklist I developed for those that submit grants. I came up with this list based on mistakes I've made in the past, right? Where reviewers kind of came back and said, okay, we weren't able to duplicate your power calculation because you did not provide us A, B, and C. And so that's what these slides are about, are these particular things that you want to make sure that you include in any kind of grant application, because reviewers will duplicate your calculations. There are a number of statistically inappropriate ways to justify your sample size. It's not acceptable to say that this is what we commonly do in the field. I'll see that a lot. That's not an acceptable answer. The idea that that's what I used last time when I got a significant p-value, that's not really acceptable because you don't necessarily have a properly powered study based on that sample size. And even though you found a significant result last time, that could have been a function of your luck. This is the effect size. I see this one a lot, and this is where I think a lot of people make a big mistake. The effect size that they use in their calculation is what they estimated in the pilot. Now, what's my problem with that? There's two big problems. One is that just because you estimate in your pilot, that doesn't mean that it's clinically meaningful, right? And two, and maybe this is the bigger problem, your pilot, think about it, is probably based on a smaller sample size. Now, it's very possible you greatly overestimated your effect size. What's going to wind up happening is you're going to severely underpower your trial now, or your study going forward. You never say that your sample size is based on feasibility. That's not an acceptable answer to reviewers. You really have to make a case that you are going to be doing meaningful science where you do have a hope of detecting meaningful effects, and say that there's no prior information to base sample size on, completely unacceptable reason. Really, that makes the case that you should be doing a pilot study. In terms of closing remarks, hopefully I convinced you that you should be doing properly powered studies. Otherwise, you're either wasting your time or just performing a scientific exercise that is destined to not have a significant p-value. Hopefully you recognize that your calculations are going to be highly sensitive to these values that you select. And so any sample size calculation that you do or any sample size calculation that you're reviewing, take all calculations with a few grains of salt. This is one aspect of my discipline where there's a little bit of an art to it. And so keep that in mind. And then also collaborate with your friendly statistician when you need help, because it's really vital, especially at the design stage. And this is how you can reach us. If you log into the CTSI portal, which I think if you go to the web page, there's a little button up here that you can click. And then there's a button for the BERD core, and there's a form that you can fill out, and that goes directly to me. And here's my email contact. And then I'll take any questions that anyone might have.
Excellent. Thank you very much, Greg. I want to tell everyone that I put the BERD portal request in the chat, so the link for that is right there. Greg, I want to thank you so much for such an interesting presentation. We learned quite a lot in a very short amount of time, and that was very, very helpful. May I ask if you could please email me the slides, and then I will email those to everyone, or at least we'll have them available for anyone who would like it. And I'm going to actually stop the recording, and we are officially done with the third BERD series, and the next one is Dr. Lamont again next week. And yes, it's on Halloween from 4 to 5:30 again.